trying to find something specific within a massive pile of information. It can feel, like searching for that proverbial needle, can it? Databases, sprawling online content, even just managing large lists. Traditional ways of searching can really bog down. Think about simply scanning through everything, item by item. That's ONN, time complexity, right? And for huge data sets, ONN means it scales directly with the data size and it just gets painfully slow. Even jumping through a sorted list with binary search, which is, much faster at OLAGN, can still take too long when you're dealing with truly gigantic amounts of data. There had to be a better way, a need for something fundamentally faster, a technique that could access data almost instantaneously, no matter how much data you threw at it. And that brings us to this deep dive, powered by the sources you shared with us. We're plunging into the elegant world of hash tables, a concept designed to achieve something remarkable, updating and retrieving information in constant time. That's O1 performance, meaning the time it takes ideally doesn't increase even as your data grows dramatically.
That's the real prize here, isn't it? That O1 capability. The material you provided really lays out the foundation beautifully, explaining not just the core idea, but also the inherent challenges that come with aiming for that level of speed, particularly something called collisions, and the clever ways computer science has engineered solutions to those challenges.
Okay, so let's unpack this.
Yeah.
What exactly is a hash table at its heart, and why is that O1 goal such a leap forward?
Well, what's fascinating here is the complete shift in approach. Traditional searching relies on comparisons, looking at an item and comparing it to the one you're seeking. Hashing, sometimes called fast searching, sort of bypasses all that. You determine the location of an item directly through a calculation based on the item itself.
Oh, okay.
You compute where it should be, and ideally you just go straight there. That's where the potential for that ideal constant O1 time comes from.
I saw a great simple example of this idea in the material. Storing a small set of integers, say 7 numbers between 0 and 10. In an array, if the numbers are 7, 3, 6, 4, 9, 1, 5, you could literally just put the value I into the array cell table I. Checking if the number 4 is there. You just look at table 4. If it holds 4, you found it. It's a direct hit, one-step lookup.
Exactly. In that simplest case, the hash function is just hi equals I. And for searching, it's perfect just one location check. But the material quickly highlights the major downside, space inefficiency. If those 7 numbers could range up to 999, you'd still put them in cells 1 through 9, but you'd need an array of size 1000 just in case.
Right.
You'd use only 7 spots and waste 993. So while that direct mapping is fast, it's incredibly wasteful if your data keys are spread out or cover a huge range. That shows you immediately need a way to map those potentially large or sparse key values into a much smaller fixed size array without requiring an array as big as the largest possible key. This is where the real hash function comes in.
So it's still fundamentally an array, but you use this hash function to translate the item's key into an index within a smaller fixed-size table. What does that function look like for more typical data?
The definition provided is pretty clear. A hash table is an array of a fixed size, usually called table size. Each item you want to store has a key, maybe a customer ID, a product code, or a word, The hash function takes that key and produces an index that falls somewhere within the array's bounds, from 0 up to table size 1. And the material stresses that a good hash function needs 2 main properties. It must be quick and easy to compute. You don't want complex math slowing things down. But the absolute crucial part is that it should distribute the keys evenly across the entire table. You want to avoid bunching, regardless of whether the original keys have patterns or seem random.
We saw some practical examples for integer keys. Truncation was one, like just taking the last 3 digits of a 9-digit ID if your table size is 1,000. So 925371622 becomes index 622. Simple enough. Then there was folding, where you might split the key, add the parts together, and then use that result, like splitting 925371622 into 9253701 and 622, adding them to get 1923. The material points out you typically need another step, like taking that sum modulo of the table size to fit it into the array.
Exactly. And that step, taking the remainder after division by the table size, is presented as a very general and effective strategy for integer keys. Key mod table size. It guarantees the result is always within the 0 to table size 1 range. Very neat.
But keys aren't always numbers. What about text, like words for a spell checker?
Good question. For non-numeric keys like strings, the common approach shown is to first convert the string into some kind of numerical value. A simple method described as summing up the ASCII values of all the characters in the string. Once you have that sum, you just apply the same modular arithmetic, the sum modulo table size. Using the apple example from the reading, You take the ASCII values for APPLE, that's 65, 112, 112, 108, 101, add them up, you get 498. Then, assuming a table size of 27, just as an example, you calculate 498% 27, which is 12. So Apple would map to index 12 in that table.
Okay, so you feed the key into the hash function, you get an index, and that's where the item should go.
Mm-hmm.
But here's where it gets really interesting. What happens if you try to insert an item and its key hashes to an index that already has something else in it?
Ah, yes, the inevitable challenge, a collision. That's exactly what happens when two different keys produce the exact same index after being put through the hash function, and you try to put them both in that single spot in the array. Since your table size is fixed and usually smaller than the total range of possible keys, collisions are basically unavoidable as you fill the table.
Makes sense.
So you absolutely need a plan for when they occur. And the material outlines the two major strategies for handling these collisions: separate chaining and open addressing.
Separate chaining seems quite intuitive. Instead of trying to put the item in the array cell, the idea is that each cell in the array is actually the head of a list, right?
Yeah.
If multiple items hash to the same index, they all just get added to the list stored at that index.
Correct. Think of the array index as a bucket, and each bucket holds a linked list of items that all hash to that particular bucket. The key %10 example with keys 0, 1, 4, 9, 16, 25, 36, 49, 64, 81 is a great illustration of this. Keys 0 and 81 both end in 0, so they hash to index 0 and are in the list at table 0. Keys 1 and 64 end in 1, so they're in the list at table 1, and, well, you get the idea.
Yeah.
Separate chaining has several advantages the material highlights. It generally uses space pretty efficiently, especially if the items themselves are large, because you only allocate space for the lists as needed. Handling collisions is simple. You just search the list at the hashed index. It can easily handle storing more items than your table size, as items just keep adding to the list.
Ah, interesting point.
And deletion is usually straightforward, standard linked list removal. Pretty clean.
Okay, so separate chaining keeps the collided items in lists outside the main array cells. What's the philosophy behind open addressing then? The material says, with this approach, the data stays inside the table itself.
That's the key difference. With open addressing, if your calculated hash index is already occupied when you try to insert, the system doesn't go to an external list. Instead, it systematically searches for an alternative empty cell within the main hash table itself to place the new item. It's about probing for a new home inside the array.
Probing, okay.
And the reading details 3 common strategies for deciding how you probe for that alternative empty cell: linear probing, quadratic probing, and double hashing. Linear probing is the most direct. If your key hashes to index and table is full, you simply check the next cell, table +1.
Just the next one.
Yep. If that's full, you check table +2 and so on, moving sequentially through the array until you find an empty slot. You wrap around from the end back to the beginning if necessary. The example shows inserting 77, which hashes to 2, but 52 is already there, so it looks at index 3 and finds it empty. Simple. Then inserting 102, which also hashes to 2, probes 3, then 4, and finally finds space at index 5.
And the material mentions a big issue with linear probing, right? Something called clustering.
Yes, that's primary clustering. It's the main drawback, really. As items collide and are placed in consecutive available cells through this sequential probing, they tend to form blocks or clusters of occupied locations. When a new item hashes into or near one of these clusters, it gets caught and has to probe its way through the entire cluster just to find an empty spot.
Ah, so it slows things down again.
Exactly. This clustering causes probe sequences to get longer and longer within those dense areas, even if other parts of the table are relatively empty. It degrades performance, pulling away from that ideal O1. It really highlights the need to distribute probes more widely.
Which is where quadratic probing comes in, aiming to solve that.
Yeah.
How does that change the probing sequence?
Right. Instead of just checking the next cell, like distance +1, quadratic probing makes the probe sequence jump away from the initial hash index, h by squares,
Got it.
+1 otter, then h +2 daughter, then h +3 daughters, and so on. Again, wrapping around the table. The example with table size 11 and h plus by 11 shows inserting 24. It hashes to 2. Linear probing would check 3, 4, 5.
But quadratic.
Quadratic probing checks 2 + 1 non tree, then 2 + 2 bot over 6, then 2 + 3, that is 9. So 2 + 9, 11, which is 0 mod 11. So it checks 2, then 3, then 6, then 0. Big jumps. By spreading the probes out like this, it significantly reduces, though doesn't completely eliminate, the primary clustering issue of linear probing.
Better, but not perfect.
Okay.
And finally, double hashing. It sounds like it uses 2 different hash functions to decide where to go.
Exactly right. Double hashing employs a second hash function, let's call it H2 key, specifically to determine the size of the step you take during probing. The probe sequence starts at H1 key, then goes to H1 key plus H2 key, then H1 key plus 2H2 key, H1 key plus 3H2 key, and so on. Each step size is a multiple of the result of that second hash function.
Oh, okay.
A critical detail mentioned is that this second hash function, H2 key, must never produce 0.
Why is that?
Because then your probe step would be 0 and you'd just keep checking the same occupied spot endlessly. You'd be stuck. This method is very effective at reducing clustering because the step size is determined by the key itself via the second hash function, leading to distinct probe sequences for different keys that might initially collide. The example with table size 11, H1x by 11, and H2x 7 by per 7 for key 14 shows this. H1 is 3, H2 is 7 minus 14 mod 7, which is 7 minus 0, so 7. It probes index 3, then jumps by 7 to index 10, 3 plus 7, 10. Different keys get different jump sizes.
Wow, okay. That's quite clever. So we've got the brilliant core idea of direct access, the functions that make it possible, and these smart strategies for handling the inevitable collisions. Where do we actually see hash tables being used in the real world, making things fast for us?
Oh, they are absolutely foundational to many computing tasks where speed is paramount. The applications listed in the sources include compilers, for symbol tables, mapping variable names to memory locations.
Okay.
Optimizing game programs, efficient spell checking, speeding up substring pattern matching, general fast searching, and even quickly comparing documents to see how similar they are. The spell checker example is a great one you can easily relate to. Imagine loading a dictionary of, say, 100,000 words into a hash table. When you type a word, the software hashes it and instantaneously almost checks if that word exists in the table. That near O1 speed is why spell check can give you feedback almost instantly as you type, even against a massive dictionary. But connecting this to the bigger picture, while hash tables are incredibly powerful for these kinds of lookup tasks, the material is very clear that they are not a universal solution. There are specific situations where hashing is simply not the right tool.
Okay, what are those situations where you wouldn't reach for a hash table? When is it the wrong choice?
Well, the trade-offs highlighted are crucial. First, they aren't ideal if your application involves a lot of insertions and deletions, particularly if you're using open addressing schemes.
Why open addressing specifically?
Deleting items in open addressing can get complicated because you might break a probe chain for other items. You often need special deleted markers. Separate chaining is better here because you're just dealing with standard list operations, much simpler for deletes. Second, if you need to process or traverse all the items in the table in a specific order, say, alphabetical or numerical order hashing is a poor choice.
Right, because they're scattered everywhere.
Exactly. The items are scattered based on the hash function, not stored in any sequence useful for sorted traversal. Third, if the data set you need to store is larger than the available memory, a hash table might not be feasible. The material suggests structures like trees might be better suited for handling data that needs to reside partly on disk. And finally, and this is related to the traversal point, hashing is fundamentally slow for any operation that requires the data to be sorted or requires finding extremes, like finding the minimum or maximum key.
Because you'd have to look at everything anyway.
Precisely. That would effectively require scanning the entire table, completely destroying the O1 benefit you were aiming for in the first place.
So what does this all mean then? We started by highlighting the problem of slow searching in the face of massive data, contrasting it with traditional slower methods like linear or even binary search. We then explored the brilliant core idea behind hash tables using a function to get direct instantaneous access, aiming for that O1 gold standard. We dove into how hash functions translate keys into array indices, faced the unavoidable reality of collisions, and saw the clever strategies computer science has developed to resolve them, from simple separate chaining to the more complex probing methods like linear, quadratic, and double hashing. And we finished by understanding where this powerful tool shines and, crucially, where its inherent structure makes it a poor fit.
And understanding those trade-offs is absolutely essential. While the O1 lookup is a huge advantage for specific operations like quickly checking if a key exists, the structure of a hash table imposes limitations, especially, as we said, when you need to manipulate data that relies on being in a particular order or requires traversing everything.
This deep dive into hash tables, drawing insight from the material you provided, really illustrates how smart foundational data structures underpin so much of the instantaneous computing we take for granted every day. From a simple spell check to complex software systems.
Yeah, it really does. And, this raises an important question. Given the strengths of hashing for quick lookups and its weaknesses for operations requiring order or traversal, what real-world problems do you think might actually require combining a hash table with other data structures, like maybe trees or sorted lists, to get the best possible performance across different tasks? Something to ponder the next time a search feels instantaneous or you use a feature that seems impossibly fast. How might they be achieving that under the hood?